Jerry, I think that you can call our speakers. He's supposed to come in.
Okay.
Tony, could you ask some questions for our today's speaker?
Yeah, I can try asking some questions, but
Yeah.
I don't have the the slides, the deck yet. So we'll see.
Yeah. Tony, could you introduce the speaker? I just sent his information to you. My slide is
Sure.
okay. I just sent to you. Okay.
Okay. Hi, Peng. And how are you? Oh, you are muted, actually.
Hi, Tony. Thanks for inviting me.
Yeah, our pleasure. So I think it's good time to start. Let me first introduce Professor Peng Wei. He's an assistant professor in the Department of Mechanical and Aerospace Engineering at George Washington University, with courtesy appointments at Electrical and Computer Engineering Department and the Computer Science Department. By contributing to the intersection of control, optimization, machine learning, and artificial intelligence, he develops autonomy and decision support tools for aeronautics, aviation, and aero robotics. His current focus is on safety, efficiency, and scalability of decision-making systems in complex, uncertain, and dynamic environments. Recent applications include air traffic control management, the ATCM, airline operations, UAS traffic management, UTM, eVTOL, urban air mobility, UAM, and autonomous drone racing, ADR. Professor Wei is leading the Intelligent Aerospace System Lab, the IASL. He's associate editor for AIAA Journal of Aerospace Information System. He received his PhD degree in aerospace engineering from Purdue University in 2013, and his bachelor degree in automation from Tsinghua University in 2007. Without further ado, let me hand over the control to Professor Wei to start today's talk.
Thank you very much, Professor Qin. It's my great honor to present here, and thanks for the invitation. So let me share my screen here. All right, so. Okay. Can you guys see it?
Yes.
Awesome. So I'll get started. So today, the topic is distributed autonomous separation assurance with deep multi-agent reinforcement learning. So my name is Peng Wei. First, this is a slide quickly cover my group. So we are the Intelligent Aerospace System Lab, or IASL. So mostly we do modeling and algorithm design for operation of air transportation and the aviation systems. So methodology, myself was trained as a control and optimization guy, especially during my graduate school. But after I joined academia, I started working on learning-based control and especially reinforcement learning, or the intersection between learning and control. So that's the methodology side. Application side, my traditional focus or past, including current focus, is on air traffic control, air traffic management. So I also work on airline operations. So some of you may know in the 90s, so operations research had a very successful time in airline operations. But now the airlines are looking at learning-based decision making. So that's another focus of my group. So the newer applications include UAS traffic management. So when we call a drone delivery or small UAS delivery, so that's the UAS traffic management side. And then we have a small research portfolio on electric vehicle prognostics. So basically to predict the vehicle flight, the flight remaining time, the battery remaining time, and so on. So today's focus will be on urban air mobility, especially we call this eVTOL, urban air mobility. So we'll speak of this in the next slide a little bit more. So last one is autonomous drone racing. So this application really allow us to combine or integrate computer vision and decision making in a high-speed, competitive environment. Sort of crowded in some places, crowded, complex environment. So today we'll focus on urban air mobility. So a little bit more about this application. When I'm in the applied reinforcement learning seminar, I want to cover this problem or problem setting or background a little bit more. So this problem or application is called urban air mobility. The core idea here are as follows. Number one, we want to use vertical takeoff and landing vehicle to transport passengers and cargo within a city. Number two, we want those vehicles to be electric powered instead of traditionally gas powered. Number three, we want those vehicles to be autonomous, and to a certain extent, we want those autonomy to be assured or even certified by the FAA or by other countries' aviation authorization. The later two are still in discussion. I mean, the first three, people are, most of the people in our community agreed those first three are pretty important. It's just we are not there yet, still working on those three. But the later later two are still in discussion. So those are relevant to the operating mode. The fourth one is, should we run these operations as an on-demand operation, like a taxi, or should we run this operation by schedule, like a transit or train, and so on, or bus? The fifth one is, should we run this operation as ride sharing, or should somebody really own those vehicles? That's still in discussion. But the goal here is the community want to build this transportation mode into a safe, efficient, and affordable transportation mode, at least affordable to a certain group of people. So that's the goal. The challenges here are multifold. So for example, number one challenge is, of course, when we take a look at this list, we need novel vehicle design, right? So we need new vehicle design, manufacturing. We need city spy-in, so urban planning and infrastructures, because not like the smaller vehicles, like the drones, it can take off and land in our backyard. This type of vehicle is larger, so we do need specific infrastructures to land and let those vehicles take off. Next one is the policy and regulations, because I'm speaking for the FAA in the US here, because FAA does not have much experience dealing with this new type of vehicle. So there is some, there must be some challenges to the current policy and current regulations in terms of safety, in terms of how to certify the autonomy, and so on, and even the electric powertrain. So, but those are indeed very critical challenges. But my group, do not do any research regarding to the first three. So my group focus on the operation side. So basically, how do we design models, algorithms, or even try out different concepts? And then we want to validate them through simulations, or sometimes even through hardware test beds. And we want to support some of the decision making for the policymakers and regulation makers. So those are our group. We are here. So those two figures represent some of our earlier work in urban air mobility community. This one is a support letter from Uber. So this letter is from November 2016. So if you are familiar with urban air mobility, Uber is one of the earliest leaders in urban air mobility. So their first white paper showed up in November or maybe October 2016. So we were actually one of the earliest group to work with them before they even released the white paper. But as all of you know, Uber at the same time is difficult to work with, especially from academia. It's hard to get their data, and it's difficult to get publications. But at least at the early stage, we were working with them a little bit. So this letter is from their chief product officer, one of the kind of pioneers of Uber Elevate. This guy is called Jeff Holden. So the second cover here is back in 2017, we worked with Airbus on this project about a year or a year and a half. So we were working on the autonomy side of urban air mobility. So three groups was invited, three academic groups were invited. So our group was one of them. So those are, I guess this is public available online. So if you are interested, want to take a read, I'll send you the link. All right, so our group focused on operations side. So what kind of work we have done? So urban air mobility research in my group. The first part we were looking at is we want to study the arrival management of this vehicle. So why do we care about the arrival of this vehicle? Because, you know, when we talk about those type of vehicles, usually when they fly in the sky, we can treat it as 2D. Because usually, you know, people often consider the airspace is leveled or partitioned into different levels. So that's why in level flight, in forward flight, usually, you know, we consider that operation as 2D. But when it approached to the arrival airport, or in this application, we call this vertiport or skyport. When approaching to the landing spot, I cannot consider that 2D anymore. So we got to consider as 3D, which means in a arrival terminal airspace, the manufacture is more complicated. So we are dealing with 3D operations. We are, you know, if the traffic density is high enough, the first bottleneck we are going to observe will be the arrival and departure, right? So those are our bottlenecks. So highly possible we are dealing with a 3D operation, more complicated maneuvers, and more crowded airspace. On top of that, usually those vehicles are very limited on their battery life. When they are going to land, their battery is already in a pretty low level. So it's kind of safety critical. So we want to make sure the arrival are safe and energy efficient. So under this category, we were working on energy efficient arrival trajectory design, or you know, online trajectory planning, and also the real-time prediction of battery discharge or remaining battery time. At the same time, we were working on arrival scheduling. It's the arrival scheduling kicks in first to deal with if we have multiple aircraft trying to land or compete with the airport resource or landing pad resource. We need to, you know, consider this with some priority with remaining battery time, and find out the you know, arrival time slot allocation, and send that arrival time slots to each vehicle, and each vehicle will use that, you know, terminal time or required arrival time as a terminal time in their optimal control formulation. So those parts are mostly optimal control and optimization work. All right, so that's that part. So if we can handle arrival, hopefully, you know, we can do the same for departures. So those pretty much will handle the terminal airspace. In the 2D or en route airspace, so when we are on a level flight, one thing we want to look at is how do we make sure those airplanes do not crash into each other. So the first idea we are working on is separation assurance. You know, under this category, we are mainly referring to decentralized type of separation assurance. But the first time we were working on this, most of our applications are like this. So you can see there's no routes, no runways in the sky. It's pretty much like free flight, or more like people walking in a mall, in a very busy mall, or Times Square, that type of thing. So this is, you know, early stage, we call this separation assurance. And then autonomous ATC, again, in early stage, we were thinking for airplanes, we have human ATCs to direct traffic in the sky, and make sure airplanes do not crash into each other. So those human ATCs is usually a centralized human watching my own radar screen and make sure the vehicles do not crash. So our early idea is, you know, can we develop a model to support, or maybe ultimately to replace this human? So this piece of software can outperform humans' cognitive limits and beat human, and beat human in directing air traffic. So we have an increased air traffic capacity. So if you compare both, I mean, they are kind of different, but somewhat the same, because both of them are trying to accommodate more air traffic, to increase the airspace capacity. At the same time, this guy looks like the decision makings on the airplane. This guy is the decision makings on the centralized agent. So here, more items here. In early stage, we work on free flight operation. We work on real-time planning or replanning. We call this computational guidance instead of offline or pre-departure guidance calculation. And then we want to do this collision avoidance with replanning, because my neighbors or intruders, they are constantly changing their trajectories. So I need to constantly do the replanning. Under this, we have structured airspace like this. We have routes, we have waypoints. At the same time, we want to have a centralized agent to do autonomous conflict resolution. And then here in early stage, we were working at a hierarchical reinforcement learning. So one centralized agent, multiple decentralized agents. So today we'll sort of cover a topic sort of at an intersection between these two. So first, we notice that if this centralized agent behave well, if I have a very smart, very fast algorithm, but it's still limited because it's still centralized. So if we want to go over this limit again, the first layer, we want to beat human cognitive limit. Next, we want to beat this centralized agent. We need to go with a decentralized version. So we will, in this talk, we will work on a decentralized algorithm. At the same time, we will work on a structured airspace like this, because according to the newest UAM concept release from FAA, they expect the near future UAM operations will be on those structured airspace. Right, so if we have this two or somewhat sort of integrate this two, we have a concept or a corresponding algorithms can help us increase airspace capacity, but there is still an airspace capacity, right? There's still a limit. There's still a capacity. So for air traffic, traditionally we have a tool to deal with traffic demand and capacity imbalance. So this imbalance can happen in different cases. So for example, morning peak, afternoon peak, those are naturally imbalanced. That's not because my capacity changes. It's simply because my demand surges. So that's one example of demand and capacity imbalance. Another example in air traffic is weather. So the weather will impact my capacity. When weather hits, my capacity will drop, and then there will be an imbalance of demand and capacity. And we all know, I guess, if we live in a big city, we all suffer from this traffic demand and capacity imbalance, right? So translation is just traffic congestion. So in air transportation, in ground transportation, how do we handle traffic congestion? I'm not familiar in ground transportation, but I know if I sit in a traffic congestion in my car, I can sit there. Either I can burn my gas or I can just turn off my my engine. So not a big deal. But for airplanes, we cannot. Number one, if we want to get into air traffic congestion, we are keep on burning the battery, which is not good, because when those vehicles, especially urban air mobility vehicles, sit in the traffic, burning the battery, so they are most likely hovering, and hovering will cost much more energy when they do level flight. So number one, we do not afford to burn my battery in a traffic congestion. Number two, it's very dangerous. So if I keep hovering there, so it might be if I burn all my battery, it might be dangerous. It fall off from the sky. So it's very dangerous. So here it's not only energy efficient, but also safety critical. So we have some tools to handle this type of demand and capacity imbalance. But put into a simple note, the effective way is to make sure the airplane take ground delay. So when we take airplanes, when our destination airport have congestions, what do we see? We see our planes kind of sit in our departure gate and are not pushed off, right? So our airport have no problem, the departure airport have no problem, but because of our destination have weather, or somewhere along our route have weather, we have to wait, at the origin, right? So origin airport. So that's the way in air transportation, how do we handle this demand and capacity imbalance? So last but not least, so we are also working on inside each mini airline, how do we dispatch those fleet? So should we run those service on demand or by schedule? So we worked on a little bit on demand modeling. If it's by schedule, we are working on some network planning, network scheduling work. If it's dispatch, we are working on near real-time dispatch algorithm. So I know our colleagues from DD is very active in dispatch algorithm development. And there's some reinforcement learning work there as well. But so our work, we haven't looked into the reinforcement learning methods in dispatch yet. Most of the work still built on my previous experience in airline scheduling and airline aircraft routing. Okay, so today we'll focus on somewhere between these two. Right, so on the left-hand side, we have a structured airspace. We have 3 routes. First route from left to right on the top, second route from right to left on the bottom, and 1 route from north to south. So we have 3 routes and 2 intersections over here. And our goal is to make sure that the aircraft, separated along the route. That's easy. And also at the intersections. That's a little bit tricky. On the other hand, we were actually still are interested in free flight operations. How, without airspace structure, without those routes, how my yellow guy can avoid all the red intruders and finally arrive to my destination. So that's the second one. But according to the recent FAA document, this one is more close to their near future operation mode. So we'll focus, today we'll focus on this one. So here's the research problem. Can we, number 1, we want to shift the conflict resolution task from a human ATC or centralized ATC to decentralized flight deck. That's the first concept. Number 2, can we design a real-time decentralized decision-making model or algorithm to enable autonomous separation assurance in a structured en route airspace? So that's, today's problem will be focused on. So some of the literature or related work or industry standard. So when we look at collision avoidance and conflict resolution, there are 2 models or products which are industry standard for collision avoidance. The first one is called TCAS. This system is actually implemented in every larger commercial jet we are sitting on. So this is basically the last layer of airplane safety. So if this system will trigger when our human ATC failed, this system will be triggered. So this system is a one-on-one system, air to air. So this is the last defense layer against mid-air collision, which is crash. And then this system will be triggered about 15 to 35 seconds before crash. You can see it's really the last line of defense of the airplane safety. And then this system will only issue vertical maneuvers, which means it will only tell the 2 airplanes, one to climb and one to descend, because within the last 15 to 20, 30 seconds, vertical maneuvers is the most effective way to avoid collision. The second tool is called ACAS-X. The first tool, by the way, is designed by MIT Lincoln Lab, as well as MITRE. The second tool again, developed by MIT Lincoln Lab. It used the same display like this. It used the same hardware, basically it's antenna on board the airplane, but different advisory logic. So basically, the first one is a fixed rule or lookup table based. The second one is a probabilistic model based. It's basically solving MDP with discrete state space. So if you are interested in this one is very, very successful implementation. I wouldn't say it's a reinforcement learning, but at least it's MDP. It's a very successful MDP application in such a safety critical aviation environment. So this guy is being tested for a couple of years now, and FAA is trying to roll out this this product to replace this TCAS. So some people say, why from fixed rules to probabilistic model? So if you think this system, if you do some Wikipedia search, there was the event that this system telling, you know, there were 2 airplanes are going to crash, you know, in Switzerland, I think. So the ATC, the human ATC, tell airplane A to go up, tell airplane B to dive or to descend. At the same time, this system is telling the 2 pilots to do the opposite. So the 2 pilots were trained in 2 different countries. One pilot was trained to always listen to ATC. The other pilot was trained to always listen to the TCAS. So that's the problem. Why we need to have this probabilistic model? Because human will make mistake, or human will sometimes delay their response. So that's why we need a probabilistic model to do this. So this is the motivation why we want to have this model to replace TCAS. At least one of the motivations, right? So those are the industry standard for airplane collision avoidance. This one tells us this is sort of still this piece of software is still in the lab, developed by NASA Ames. So this software called Auto Resolver. It has a simplified version called T-Safe. The idea here is this is a ground-based system, a centralized system. It is used to resolve conflicts or prevent loss of separation, which means this system will be triggered earlier than this guy. So this system will usually be triggered 1 to 2 minutes away, sometimes 30 seconds, but usually 1 to 2 minutes, 1 to 5 minutes. So when we find problem, so this system is trying to support or ultimately replace human ATC. So the planning horizon is similar to human ATC's planning horizon. So this is this system. So our work is air to air, so vehicle to vehicle, not one on one, but one on many. So our work doesn't issue vertical maneuver, but really like this, our work is trying to issue speed changes because in the en route airspace, human ATC will rarely issue, circling the airplane, we call airborne holding, will very rarely issue airborne holding or vectoring, so sort of a zigzag type of pattern. Because in the en route, we don't have to do that because en route is relatively a simple example. We will see those airborne holding, the circling, the zigzagging near the airport or near the vertiport. So today we'll work on speed changes only. So more about related work, reinforcement learning in ATM, air traffic management, or ATC. So there are quite a few work in air traffic flow management. So flow management is what we call how do we balance demand and capacity, or basically how do we reduce congestion, right? So there are at least there are multiple work on that. So this group is from Brazil. So they use reinforcement learning to issue ground holding advisories. This group is from my colleague, Professor Kokendorfer at Stanford. They use the MDP formulation to do this work. And then Professor Michael Ball, and now the Professor Alex Astis. They use multi-arm bandits to issue ground holding decision making. But all those work are more or less strategic, right? So if we want to issue ground holding, which means the airplane are still on the ground, which means it's not safety critical. But here we are one of the earliest, we should say the earliest group to use learning-based or RL-based approach on a tactical air traffic control or separation assurance. So here we will work on our first paper has both speed and route advisory, but today we'll focus on speed advisory. So some people will ask, hey, you know, we are using a learning-based control or learning-based planning model to do such a safety critical, to address such a safety critical application. So how can we guarantee safety? So we'll speak of that, you know, hopefully in the discussion time. So we'll come back to that topic. So our approach is, I guess, for this group is very standard vanilla type of, A2C or multi-agent reinforcement learning. But allow me go through this. So our plan is to formulate this problem as a multi-agent RL and solve it with A2C, actually PPO. So a little bit about A2C. So this is a policy gradient method. We have an actor over here trying to update the policy and select the optimal action. We also have a critique here to evaluate how good the current state plaza action is. And then this critique will also generate the TD error. The TD error will be used to update both my value function as well as my policy gradient. And as we know, advantage is used or actually designed to stabilize the learning. And our multi-agent reinforcement learning setting is cooperative. We assume every airplanes are friendly. We don't want to crash into each other. So that's our assumption. So everyone's a cooperative. And here we use a centralized learning distributed execution method. So if you follow multi-agent RL closely, you will see one of the recent paper from Chris Amato's group from Northeastern, I think. So they recently have a preprint to evaluate or compare different settings of centralized learning and decentralized execution, which is pretty informative. But we will use this setting as well. So some of the assumptions to make our life easier, but actually all the assumptions are valid. The first one is all the aircraft stay on their own route. Although when we going to the airport, getting close to the airport, it's not true because sometimes, most of the times the ATC will issue either ground, airborne holding or radar vectoring, which is sort of the zigzag you see from airplane trajectory. But in en route, this is true. Most of the airplane will stay on their own route. When they change their altitude, the pilot has to ask the ATC to give the altitude clearance. So it's, even change altitude is kind of, not straightforward. So most of the airplane, all the airplane will stay on their own route. Number two, the aircraft will enter the sector following a random distribution. So this is also true because I cannot ask the airplane to enter my sector by schedule. I cannot tell this pilot, hey, enter my sector at 3:05. That's, and 35 seconds. That doesn't make sense. So we don't schedule that because that's tactical system. We need to handle whatever comes to my sector. We may have some hands-off and communication with neighboring sector, but in general, the entering is random. Number three, so here we focus on two-dimensional airspace model. Also true, most of the en route airspace is, we handle that as a two-dimensional model. So here is a simple mock-up for the sector. So we actually have, more complicated use case and demonstration on YouTube. But today, for simplicity, I'll use this example. So we built such a sector model inside a simulator. So this simulator is called Blue Sky, developed by TU Delft in Netherlands. So this Blue Sky is open source. So we have some freedom to build my, my own sector. So this is the sector look like in the video. So multi-agent RL formulation, the state here, I'll go a little bit quickly. So for reinforcement learning, we have a couple of key recipes or key ingredients. So we have state here, we have action here. So state is like in control. We also have state variables. Action in control, we have control input and reward. In optimal control, we also have that cumulated reward along the way, together with terminal reward or end reward. So in this problem setting, our state, the first vector here is my own state. So which means, I want to know what my current state is, including my position, velocity, acceleration, and so on. So anyway, this state is describing my own state. At the same time, I want to take a look at the K closest aircraft. In this case, simple example, I want to take a look at my 3 closest aircraft. So those are all their information. So I called, if I stitch them together, I call this vector SI. My own state, I call this SO. So some colleagues may ask, hey, what's going on here? Why I'm only interested 3 or only K? But because I showed you the video, I mean, in a less busy period, maybe the aircraft is sort of, dangerous to me, or could collide with me. Maybe there are only 2 or 3 in this sector. So we should only consider 2 or 3. But when it's busy, when it's crowded, maybe 3 is not enough. Maybe it's 7, maybe it's 8, maybe it's 10. But it should be varying. It shouldn't be a fixed number. So how can we handle this varying number of multi-agents? So I'll show you later. So we do have a mechanism kind of become sort of standard in multi-agent reinforcement learning. So we have that to handle varying number of intruders. So action, as we spoke, so we only consider the speed changes. So we have slow down, speed up, and hold the current speed. Reward. So this is a simple case. We penalize when airplane getting too close, lost their safe separation. When it's far away, above 10 nautical miles, we consider they are safe. Somewhere in between, we do some minor penalties there. So this reward in our current publication becomes a little bit more complicated. So we will, penalize the speed changes. Like every time we speed up and slow down, we'll issue some penalty. So that worked well as well. Right, a little bit more about my simulation environment. So one episode is one entire play through the simulation. This episode will conclude at terminal states. But what are my terminal states? Terminal states are any aircraft reaches conflict state, or all the aircraft safely exit my current sector. We call this go state or exit state. So learning efficiency, scalability, and stability. So we use centralized learning distributed execution. So in this case, only one neural network is learned. Again, so simple case. So now we have versions that can multiple neural network can be learned. But in this talk, one neural network is learned, which means all the agents behave the same. So the same neural network weights are distributed to all aircraft, and this reduces the number of parameters. So A2C, advantage actor critique, we also use PPO to further stabilize the learning. So here is the simple architecture here. So we talk about this part is my own state. And this part is I stitch up together my K closest intruder. And through one layer of fully connected layer, so I have an abstraction here. This is still my own state. I put them together, go through, in this case, 2 fully connected layer. My output is my policy and also my value. So then I can go ahead to do my A2C. So in this case, suppose I I want to look at K closest, in this case, 3 closest intruders. So in this case, if it's 3, I'm pretty sure the length of this vector is a fixed length, right? So according to the previous example, it seems like it's 6 multiplying 3 it's about 18. But now we also talk about we do not want a fixed length, a fixed number of intruders. We want to consider varying number of intruders. So in this case, we replace this layer using LSTM, or we also tried attention. We tried both, and those two worked well. So those either LSTM or attention can encode the varying number of intruders to a fixed number of contacts. So in both attention and LSTM come from natural language processing. So both of them, or either one of them, will encode a varying number of lengths of state vector into a fixed length of state vector. So here we will always have a fixed length, and then the remaining will be the same. So if you are interested, our paper is on the archive, so I'm happy to share as well. So case study. So here we consider 1 en route sector, 3 routes, 2 intersections. 30 aircraft randomly enter the sector. Here's nothing optimal here. It's just we call this optimal solution, or maybe we should call this ideal solution. All 30 aircraft will exit the sector without any conflict. So that's our, this will make us happy. The results, so I'm showing the learning curve here, and we see, gradually all 30 aircraft can exit safely, and then conflicts, gradually the conflicts will reduce to 0. So the multi-agent RL model converges to the optimal solution with about 20K episodes. So this is early version, so about a year and a half ago. So this 20K episodes, which is equals to 2 days of training, so wall clock time. So if we do a lot of applied reinforcement learning, we know one bottleneck from reinforcement learning, when we even have a simulator, is to actually run that simulator, how fast that simulator can run. So now we have a better version. So for example, we have parallel, computing version. We can run the simulator in parallel, and we have some other tricks. So now 2 days become 10 minutes. So with 10 minutes, we can train an agent that direct a much more complicated vector sector than this. Right. So and we put this converged model onto 200 new episodes, and the result is about only 1 episode didn't give the quote optimal solution. So we were looking at that model, and looks like there's naturally no good solution to that. But for the other models, it worked pretty well. So that goes back to our kind of comment before. So hey, we are using a learning-based approach to trying to scale up, trying to handle one versus many scenario. So that's why we want to lean on the learning-based approach. But seems like this learning-based approach is not 100% safe. So how can we say something about safety of using RL at a safety critical application? So hopefully we'll have time to discuss that in a little bit. All right, so on the left-hand side, we see this before. This is 2 intersection. At the same time, we can do merging as well. Click this. All right, so those are the 2 routes merging to 1. I guess in ground transportation, if you think about highway, if you think about there's a highway and there's a ramp merging to the highway, this should be similar as well. Right, so summary here, we proposed a real-time distributed separation assurance algorithm for structured en route airspace. We formulated this problem as a multi-agent RL. We solved it using a vanilla A2C and PPO, and we used a setting called centralized learning, decentralized execution, and the simulation results showed the algorithm is somehow promising to prevent loss of separation in a small scale use case for high density air traffic. And we still have time, still curious about this free flight operations. So some of you may see, hey, this yellow guy is doing well, always going to his favorite store in this busy mall. But hey, look at those red guys. The red guys are constantly crashing into each other, right? So can this, algorithm scale? Can we put this algorithm in every players in this, playground or in this mall? The answer is maybe we can, at least for up to 30, 40 aircraft, we can. Some people may ask, hey, I've seen this video before. The video showed by some, cooperative control people or optimal control people always form a perfect whirl or swirl in the middle, and each one will go to their destination. But why here we don't have that? Well, because in this case, we injected uncertainty in this. So each aircraft, have some uncertainty because MDP formulation, RL formulation naturally can deal with model uncertainty. So we put some uncertainty there. That's why that circle is not formed. But yeah, so this algorithm is somewhat scalable. If we implement this algorithm to urban air mobility, so notice we don't have route here. We only have, those vertiports. So if we run that algorithm in a mock-up New York City, so we have this results. So when I presented this at NYU, my colleague will ask me, hey, how many seats does each airplane have? So I say, oh, usually we are thinking 2, 4, or 8. And my NYU colleagues were laughing. So they said, no, this capacity is too low. So at peak hour, if it's really 4 or 8, look like we have 20 aircraft here. 4 multiplying 20, we are only providing 40 seats, or we are only providing 40 seats for the commuters. For NYC, that's not good enough. So they were suggesting we can sacrifice the airplane speed or velocity, because currently their airplane data is exactly the same with the published data from Airbus. So they suggest in a NYC scenario, we can let the airplane to fly slower. So in that case, we can accommodate more airplanes in the sky. At the same time, they are aware the airspace is not 2-dimension, it's really multi-dimension. So with multiple dimension, multiple height or altitude, possibly we will provide more seats for the commuters in NYC. So this is another example. We further sort of build some cells or structure in this airspace, and we can accommodate more aircraft in this case. So our group, mostly we work on modeling and computing side, but we do have a small task, work on autonomous drone racing. So this is a test bed we built, back in my lab when I was still at Iowa State. But now, after I moved to a new university, we are starting to build this again, and we plan to demonstrate the algorithm in an indoor environment as well. So this is all I have for today. So if you have any questions and comments, we can discuss. Thank you very much for your attention.
Thank you, Peng, for the wonderful talk. A lot of information there. As I said in the chat box, we can please feel free to pose any of your questions in the Q&A.
Right.
Actually, I do see there's a question here from an anonymous attendee. So the question is, what is the exact reward function with penalty? And what are the algorithms in your case study? Is it a generative model or online learning?
I see. So the exact reward function is pretty simple. Let me show you over here. So it was set in a kind of straightforward case. So here. So when there is a conflict, we have -1 here, where conflict means the two aircraft are within 3 nautical miles. If within, if it's you know, far away than 10 nautical miles, there is no penalty. If it's 3 nautical miles and 10 nautical miles in between, we do have a small penalty there. So I guess that's for the first question. But I think there's, let's see. So what are the algorithms in your case study? I think the algorithms we use vanilla A2C and PPO. So that's the algorithms. Is it a generative model or online learning? Not sure. I think it's, you know, good question. So let me maybe describe the setting a little bit more. So we have a simulator and we start with, you know, initial neural network. We deploy those neural network into my airplanes. In that simulator, we let them run in the, so let me show it here. Yeah, so, okay, so we have an initial neural network. We deployed it and we let it run and we collect those conflicts information, negative rewards. And then we collect all those data. We train the neural network, a single neural network. After the updates, we deploy the weights to the individual vehicles again, and we let the simulation run again. And you know, by following that, we have this learning curve. So hopefully that's clear.
Peng, I actually have a follow-up question regarding
Right.
the reward function.
Yeah.
So if you could move back to that that slide,
right.
In the MDP formulation. So your reward function, it I think it depends on basically two agents, right? Because we need to measure the distance between the current agent and another agent. How do you calculate the reward at a global level, or because at the individual level, for example, maybe your current agent is close to more than one other agents, right? Multiple other agents, and in that case, then do you just accumulate those penalties, or like how does that work?
I see. That's a very sharp point. So in this case, we were you know, realizing in this case, if we want to model this explicitly using a mathematical model, our reward function actually has a lot of coupling with other agents. So if we really formulated this as a multi-agent RL, the reward function has coupling. The coupling will be a nightmare for scalability. So what we did was, we use this little trick. So we model, my own state as SO, and we describe, in this case, the K closest aircraft, because only the closest guys may, crash to me. So we only consider this SI and SO, and then we put them together into the input. So together, those are my input. And to answer Tony's second question, so if two of the aircraft are both within 3 nautical miles, usually we didn't observe that because it could happen, but usually will happen. There's one aircraft will be within my 3 nautical miles circle first. Once that guy is within my 3 nautical miles, we consider this is a negative reward, and this at least this agent simulation will be terminated. So rarely it will be 2 agents entering my 3 nautical mile circle. It's pretty rare. It could happen, but pretty rare. Well, I guess we didn't consider that in our framework.
Okay.
Yeah.
Yeah. Yeah. One other question is about the state. So so I remember you mentioned that you have the assumption that every agent follow their route, right? Is that route information within a part of the state information, or because
Yes.
Okay.
That's right. So I believe this P is which route I am on, or which path I'm on. So with this P,
Okay.
and also with this distance to the goal or distance to the exit, so I can get the position of this vehicle.
Okay.
Yeah.
And since the state consists of the information of your own ship and K other closest aircrafts, right? So
Right.
that part that represents other aircrafts, I imagine that is constantly changing because the identity of those closest aircrafts could change from time to time.
That's right. In our earliest formulation, if we pick K as 3, this closest 3 are always changing based on where I am. But then in our newest implementation, which is attention mechanism. So basically, we use a kind of attention network to encode this intruders. We can actually to look at the entire sector. Although we probably don't need to encode all the aircraft in the sector because some of them will never, I guess, crash into me. But the attention, we did try to use attention to encode a very long list of intruders, and the results are pretty promising.
I see.
Yeah. Also, when we use LSTM, we noticed sometimes it has some bias. If we use LSTM to encode the 3, it will pay more attention or have more weights to the last one encoded in that LSTM. But attention doesn't have that issue, I think, from our numerical results.
Yeah, regarding LSTM, actually, yes, I also have a question. Is there any particular ordering information in that list of other aircrafts? Since if you use LSTM, you are sort of like imposing some kind of a ordering, right?
Yes, that's also a great question. We do have some ordering consideration. So details described in the paper, but so simply put, there is the ordering, especially for LSTM. That ordering is pretty important, actually.
Okay. Maybe by the distance from the current aircraft or something.
Right. So I may have a figure. Is by the distance to the intersection. So let's see. So there's a figure. Okay. Yeah, so this somewhat describe the ordering. So for example, one way to order so this is an illustration on 3 closest aircraft. So I can order them by relative time to the intersection or relative distance to the intersection. So those are just two examples of the ordering. So one, I can name this guy 1, 2, 3, or I can name this 1, 2, 3. So
Okay.
yeah, we did some ordering kind of trials. Yeah. Another might be interesting figure. Let me see if I can find it here. Is right. So this figure shows when we add some penalty to speed up and slow down, the blue guy is after adding the penalty. So we can see after we're adding that penalty, most of the actions will be hold the current speed. About 92% will say, let's, keep the current speed. If we don't add that penalty, we can see it's always asking airplane to slow down and speed up. So that was another slight change on the reward function we did.
So is it from an operational perspective, is it more desirable to have a higher percentage for hold? Instead of,
it's more desirable not to have airplane change their speed frequently.
Okay.
Right.
Okay. Jari, are there any questions from the?
It's more desirable.
I think no. That's all the questions we have.
Okay.
So regarding the are there any questions? Okay. Yeah. So regarding the action space, I noticed that right now the action space is just about the agent itself.
Right.
But since we are in the multi-agent paradigm, do you have any plan to incorporate, for example, the action of other agents into your action space so that more coordination can be achieved?
Right. So that's another great example. So let me try it. So basically the joint action. Let's see. Right, so I couldn't find his recent archive paper. But I think the answer is yes. So in his paper, he was evaluating the different setting of, centralized critique, decentralized actor, or decentralized critique, decentralized actor, or I remember maybe centralized critique and centralized actor. So when we have a centralized actor, the action is joint, right? So that centralized actor is basically outputting, hey, I found the best joint action for all of you is you do this, that guy do that, and whatever. But when we have a decentralized actor, I think the output will not be joint action. Yeah. But there are some very nice comparison in this setup. So centralized or decentralized actor, and also the critique.
Sure. Yeah.
Yeah, thank you. I think that's all, and it's time to end our talk.
Great.
Yeah. Great. Yeah, we are just on time. Yeah. Yeah. Thank you so much, Peng, for bringing us this very excellent work on the multi-agent reinforcement learning and aircraft management. Yeah.
Absolutely. Thanks,
And,
Professor Qin. Thanks, Jerry, for your organization and invitation.
Yeah, thank you for your talk, and thanks Tony's discussion. Thank
Yeah,
you.
I enjoyed it, the discussion with Tony.
Glad to hear. Thank you. Yeah.
Yeah.
Bye for now.
Right, bye.